Section E from our 15.3, the normal distribution lecture. And before moving into that piece, I just want to summarize some of the things that we did in our class session today. We started by focusing on the empirical rule for the good old bell curve and started with just some generic values showing what? Kind of the percentages of the data that falls between different intervals. We noticed that the normal distribution was perfectly symmetrical about mu, the mean. 50% of the data below, 50% of the data above the mean. And then we also said between various standard deviations, notice sigma, our standard deviation, one standard deviation up, another standard deviation up, so on and so forth, we could identify what percentage of the data or the random variable, what the probability of the random variable is for falling between these values. And so we did a whole series of questions. And this again was with a generic structure for mu and sigma, the standard deviation. We then went to the classic standard normal distribution curve that has what? A standard deviation of 1 and a mean of 0. And we took all the pieces that we had up high, and now what did we do? A mean of 0, excuse me there for the cord getting in the way, sorry about that, and a standard deviation of 1. So what does the x scale become? 0, 1, 2, 3, moving up to the right, working down to the left, -1, -2, -3. So this little point right there represents what? 2 standard deviations above the mean. And the nice thing is, because the standard deviation is 1, our scale is actually perfect. It represents standard deviation. It's really cool, and that's one of the nice functions about the classic normal curve. With a mean of 0 and a standard deviation of 1, we get a very nice representation along the x-axis. Now, we also said, well, most distributions don't have a mean of 0 and a standard deviation of 1. How do we go ahead and work our way through that? Well, it turns out with just a little bit of knowledge, we can map this curve and this x-axis scale to any other x-axis scale as well. So let's talk about that. And we did this right at the end of class when the bell hit. In this section, part E, we went with another normal random variable, but now we said the mean is 10 and the standard deviation is 2. And I asked you to mark the intervals on the bell curve as appropriate. Well, what went right in the middle? 10. It's the mean. And then what do? Well, we just count up standard deviations and count down standard deviations as we go each ticky mark. A standard deviation in this case is 2. 10 plus 2, 12. One standard deviation above the mean. 14, 2 standard deviations above the mean. 16, 3 above the mean. 1 below, 10 minus 2, 8. 2 standard deviations below now sits at 6. 3 standard deviations sits at 4. And so in the past we said, well, what's the probability that we were within 1 standard deviation of the mean? It was 68.26%. Well, in this new normal variable, we're saying that the probability of this random variable being between 8 and 12 is equal to this. Remember, 12, 1 standard deviation to the right. 14, 2 to the right. So all these percentages that we saw in the normal bell curve still applies. And so what's really happening is we are again measuring things in terms of standard deviations. Our scale is a little bit different because the standard deviation itself is different, but the bottom line is all these percentages under the curve are all going to run according to the same type of pattern. So what I'd like you to think about is this particular problem. I asked you in my email that I sent out, I want you to change one thing. What's the probability in this case that x takes on a value between 5.5 and 17? Between 5.5 and 17. And we can use the normal CDF, but in this case, we need to use our last 2 parameters. Remember, normal, CDF, lower, upper, mean, standard deviation. That's what goes in to the calculator. So in this case, what will we do? Well, we're going to run, and you can see it written down here, but let's do it in a little bit bigger handwriting. Normal CDF 5.5, 17, 10, 2. And I'll go ahead and bring over my calculator. And second dist, normal CDF, and here we go. 5.5, comma, 17, comma, 10, comma, 2. And I come up with an answer of 0.98754. Now, earlier in class, I had asked you to take a look at one of the problems that we did, and that was, excuse me 1 second. I asked you to calculate the probability of your normal variable, standard deviation of 1 and mean of 0, being between negative 2.25 and 3.5. And we came up with 0.9875, the exact same answer as we just got. Now, why is that the case? Well, here's what I'd like you to think about. The value 17 is how far away from the mean? It's a distance of 7. How many standard deviations is represented by 7? Well, each standard deviation is 2 units. 7 divided by 2 is 3.5. 3.5 standard deviations above the mean. 5.5, when I take that, subtract it from 10, I get 4.5. And by the way, 4.5 is what? 2.25 times 2. It's 2.25 standard deviations to the left. And so here's what I'd like you to think about. If you run normal CDF with negative 2.25 standard deviations to the left, 3.5 to the right, positive 3.5, which is what we did before, but let's look at it again. So here we go. Second, calc distribution, normal CDF, negative 2.25, comma, 3.5. And just for grins, I'll just go ahead and put in my other two parameters, 0, comma, 1. Don't need to do it on the old calculators, but we'll do it. And what do you notice? The exact same answer comes out. Normal CDF, negative 2.25, 3.5, with parameters 0 and 1, is the same as a normal CDF in terms of the value coming out, 5.5, 17, 10, and 2. Why? Because 5.5 is negative 2.25, or 2.25 standard deviations to the left of the mean. 17 is what? 3 standard deviations to the right. So it turns out that we can take and think about this. Well, what am I doing here? There's 1 SD. This distance is 14, represents 2 SD. And so what I can do is very nicely, what you can see is if I took this grid and overlaid it with this little grid that we have here before, all my percentages would be the same, just be my values on the x-axis that would be a little bit different. My 0 that I would happen to have here now becomes a 10. My 1 standard deviation now becomes what? The value of 12. 1 standard deviation, 10 plus 2, so on and so forth. And so what you're hopefully seeing is a very distinct pattern and a nice way in which I can take any standard normal distribution and translate it into our classic normal distribution. In other words, I can map these values that I have here into standard deviations. And that's called normalizing your random variable. And what you'll find out is, and this will be called a z-score, and a z-score is measured in standard deviations. A z-score is nothing more, and I'll have to write this a little bit bigger, I'll do it over here, is equal to your value of x, whatever you observe your random variable to be, minus the mean. That tells you how far apart you are from the mean. And then when you divide that by the standard deviation, x minus mu over sigma becomes the number of standard deviations that you're away from the mean. Let's do 17 as an example. 17 minus 10 over 2 equals 7 over 2 equals 3.5, just like we talked about. 17 in that example on our prior page is 3.5 standard deviations above the mean. Hey, 5.5. 5.5 minus 10 over 2 is equal to what? Negative 4.5 over 2 equal negative 2.25. 5.5 is located negative 2.25 standard deviations from the mean, or 2.25 standard deviations to the left of the mean. So what I'd like you to do is do a little bit of comparison here. On the left side, I have a classic normal CDF with a mean of 0, standard deviation of 1. And over here, I have normal CDFs with different means and standard deviations. I'd like you to compare them and see if they are equivalent. First things first, you could run them through your calculator and verify that you get the same answers. But what I'd also like you to do is figure out, okay, is 12.5 1.25 standard deviations above the mean of 10 in this problem? Think about it. And do the same with these others. Again, this is called standardizing your random variable. You're taking these numbers that you're given, whatever they happen to be, and now you're turning your random variable into a measure that represents standard deviations. One more piece to practice is just look down here. Hey, I have a problem where I have a mean of 16, a standard deviation of 4. Please tell me what the z-score is for 22. Well, 22 is what? 22 minus 16, it's 6 units, whatever our units happen to be, above the mean. Standard deviation of 4. 6 units above the mean is equal to 6 divided by 4. 1.5 standard deviations above the mean, a z-score of 1.5. Please do the same with the other two problems, and with this body of knowledge, you should be set to knock out all of the homework problems that we have.